Welcome back to another video here. We're making slow and steady progress on the book. We're more than 80% of the way there. We're switching over to using it the way the author recommends. The author wants you to use a Google Colab notebook rather than doing it using your local hardware. And I'm that guy. I want to see it fail. I want to see the error messages. So I did it on my local hardware. And one of the error messages I got was the Jupyter Notebook kernel kept consistently crashing. And the reason I believe that happened is I just don't have enough in the tank. I have a decent gaming computer. I can run the latest games at good settings. But this is something important to know about AI and ML. Is it's very, very power hungry. So no matter how good of a gaming computer you have, it's not going to be enough. We did a ChatGPT conversation, and you could spend $25,000 on a custom home setup, and even that wouldn't be enough. This is billions and billions of dollars are going into this, and it's $1 trillion industry, AI, for training these models and the hardware and everything. So what you can do at home with your own hardware has a lot of really hard limits that show themselves really fast. But the good news is there are some good options for you to do actual, real, impactful things for cheap. One of the things you can do is use Google Colab Notebooks. Google Colab Notebooks give you a free limited use of a GPU and even a TPU, which is the next level in the cloud. So it gives you a free access to these really powerful hardware in the cloud. And then if you want to do something professional, if you really want to make a real product, you can pay and you can get pretty much as much horsepower as you need. I would be willing to bet that there's companies out there spending millions and millions of dollars right now just on cloud training. So let's ask ChatGPT that. Then we're going to get this notebook back to the state, and then we're going to get some reading done. But let's start off with a question for you here. So my question is, can you give me a list of companies or entities or whatever else that you would speculate could be spending at least $1 million per year on purchasing cloud access to tools that would be required to develop and train artificial intelligence?
Sure. Here's a speculative list of companies and entities that could be spending at least $1 million per year on cloud services for developing and training artificial intelligence. Technology giants Google, Alphabet Inc.
So it's just a lot. All of them are going to be doing it. All right, well, let's do this. Okay, great. Now narrow down the list for those who might be spending 100 million or more per year. Yeah, it's basically the same list. See what I mean here?
Sure. Narrowing down the list of those entities that might be.
Okay, now narrow it down to those spending $1 billion or more per year. Even that, there's going to be, it's the same list.
Narrowing it down to those entities likely.
All right, now narrow it down to 100 billion or more a year. Narrow it down.
Currently, no single entity is known to be spending $100 billion or more per year solely on cloud services for AI development and training. Even the largest tech giants' overall annual spending across all operations, including AI, cloud services, R&D, etc., typically does not reach that scale individually.
They have their own stuff.
Closest candidates for extremely high expenditure, though not necessarily $100 billion solely on.
Is that because there's a point where they switch over to their own stuff and they no longer do it in the cloud? If that's the case, why? Because why is Google spending so much on cloud services? Why don't they just build it at home?
There are several reasons why even tech giants like Google, Microsoft, Amazon, Apple, and Facebook, Meta, might continue to spend heavily on cloud services despite having their own infrastructure. 1. Scalability and flexibility. Scalability. Cloud services offer the ability to scale up or down quickly in response to demand. This flexibility is crucial for AI development, which can have variable computational requirements. Cost management. Cloud services can be more cost-effective for handling peak loads without the need for permanent investment in physical infrastructure that may be underutilized most of the time. 2. Speed of deployment. Time to market. Using cloud services allows these companies to deploy and test new AI models and applications faster. Building or expanding their own data centers takes significant time and resources. Innovation. Access to the latest technologies and services offered by cloud providers helps maintain a competitive edge. 3. Specialized services. Advanced tools. Cloud providers offer a range of specialized AI tools and services, such as machine learning frameworks, data analytics platforms, and pre-trained models that can accelerate development. Integration.
All right. Well, I'm just getting distracted here. So let's get this stuff to work. It should work now. So we can do a, so we can click the icon here, and it should mount the proper drive. Hopefully it's thinking about it. Yep, so let's permit it. Let's permit it. Not sure how to permit something. All right, looks good to me. And I definitely should have done this in my other account. This hogs up a lot of space on my drive. All right, so it's now mounted. So you should be able to do this perfect. Now this one. I notice how for this one we don't get that error anymore. That's because we're using hardware in the cloud that belongs to Google that was configured correctly and has that extra thing enabled that was not enabled on my local hardware. Okay, so now the events DF takes about the same time, if not a bit longer, doing it here. So this is a good time to get some reading done. And let me take a quick break. I'll be right back. All right, I'm back. So let's get some reading. So in the code above, we are pushing through the encoder model batches of 100 entries until we finalize all our training data. The result is the training logs represented in the latent space as the shape of the array reflects. Now it is time to write this array in a file. We are not writing in a CSV or text fine, but in, and this should say file, I think, rather than fine, but in binary format, which we will recover later when we need to read. The advantage of the H5 format is that you can read a position of the file at any point in time without the need to load the entire file, which is extremely convenient for an incremental training we will do in the GAN. There we go, looks good to me. Reading a specific position from the H5 file. We are now going to switch to the GAN notebook. Okay, so I'll definitely put a pin in that and see this notebook all the way through, and then, you know what, I can pull up the other one. So if I do here and I go duplicate, all right, and then I go locate in drive. Okay, so it's locating there. So this is interesting. Huh. Oh, it bricks it if it's in another tab, I guess. Okay, well, Not sure what's going on here. It should be, yeah, so here's the location. Let's do a search for this file name. Okay, so this is better. We can see the symbol here. This is what I was looking for here. This. So now we can open the other notebook. And we should be able to get a start on this one. So if we go to rename, or sorry, if we go to runtime and we go to disconnect and delete runtime, and then clear all output. All right. And then click connect here. So you can only have one session at a time unless you pay for Collab Pro, which costs you $9.99 per month. And I do pay $20 per month for ChatGPT. So I'm kind of at an interesting inflection point in my life right now, because I used to never want to pay for anything like this. But I see the value in paying for ChatGPT. So it's probably a good time to shop around, and if there's something that makes more sense, something that includes ChatGPT basically, because this comes with AI enabled auto completions and code generation, and it's half the price, and you get a terminal, you get access to the GPUs and stuff. So it's a good time to shop around, I think. Okay, so we have too many sessions, so I'll close this session here, and then I'll click cancel. Oh, and I wish I hadn't closed that. Let's click manage sessions and hopefully get this one back. Okay, so we were able to get this one back. All right, unfortunately, we ruined the cell from running. All right, so let's do let's do a restart session and run all. Yeah, so now it's running all of them one by one. Okay, so hopefully that's it seems to take a bit longer on theirs than it did on mine. All right, well, we could keep reading while that's going. So now we are going to switch to the GAN notebook, UC9 log generator GAN .ipynb, so a Jupyter notebook. At the beginning, it has a similar structure as in the autoencoder notebook, but now our input data are no longer the raw logs, but the latent space encoded version of them captured in the file we just produced at the end of the previous notebook. Looks good. Some new variables to highlight. Latent underscore lane, the length of the latent vector. Noise underscore len, the length of the input vector in the generator. This input vector will be filled with random noise values and will be the seed for the generator to produce hopefully realistic log messages. We have a new function worth mentioning that is intended to load a batch of data from our binary H5 file and use it for training. All right. We explained earlier the concept of the batch generator, which had a yield instead of return. But this function does not have such structure. What happened? What happens here is that the training of a GAN is special. We are going to train two neural networks at the same time, so the process is not as straight through as in the previous cases. Effectively, we are going to deconstruct the training process: forward propagation, loss calculation, gradient descent calculation, and back propagation, and run each of the steps manually. It is more complex, but it will also give you visibility on each part of the process. You will learn how, with TensorFlow, you can manipulate and create custom behaviors that allow us, in this case, to train two networks, the generator and the discriminator, all at once. We need the decoder to produce readable logs from the very compact but 512 dimensional latent space. As you can see below, the decoder is exactly as we did before, and we are going to load the same weights obtained in the training. There we go, looks good to me. Now it is time to define and build the models for the generator and discriminator. After trying various options, I ended up using plain feed-forward dense models. Ultimately, regardless of the fact that we are working with what at origin are sequences of text inside the GAN, we are simply dealing with vectors. We do not need to build more complex architectures such as LSTM or even CNN. It is just a vector as input, and we need, in the discriminator case, an output saying 0 or 1, real or fake. The generator simply needs to receive a vector, noise, and generate another vector, a log in the latent space. For both cases, it is feasible to use feed-forward dense networks that likely will train faster, and we can identify faster if the whole system is converging or not. With that in mind, the following are the simple architectures for generator and discriminator. All right, and let's do what the Romans do. Well, let's do what I do and paste this into ChatGPT for some reason. I don't know why.
The image depicts the architecture of a neural network generator. Here's a breakdown of its components. Input vector. The input of the generator is a vector of random noise with dimensions 1 times 1281 times 1281 times 128. Dense layers. The first dense layer transforms the input vector from 1 times 1281 times 1281 times 128 to 1 times 10,241 times 10,241 times 1024. The second dense layer reduces this to 1 times 5,121 times 5,121 times 512. The third dense layer further reduces it to 1 times 5,121 times 5,121 times 512. Output vector. The final output of the generator is a vector with dimensions 1 times 5,121 times 5,121 times 512. This structure is typical in a GAN, generative adversarial network, generator where random noise is transformed through a series of dense layers to generate a desired output vector. If you need further analysis or have additional questions regarding this architecture, feel free to ask.
Isn't that amazing? Like, this is seriously impressive because it doesn't say anywhere that this is a neural network generator. It certainly doesn't say anywhere that it's a generative adversarial network. Like, it just knows. It just knows what it's looking at. Like, it's impressive both that the author was able to write a clear enough diagram and that ChatGPT is advanced enough to actually be able to read it. Like, isn't that insane? Like, can anyone watching this, like, if I just showed you this and nothing else, would you know that this was a neural network generator and that the structure is typical in a generative adversarial network? Like, would even, like, people who are, like, really advanced in this, like, know that? Like, would a college grad know it? Like, maybe a PhD person would know it, but, like, am I the only one here that's impressed by this? This is like one of the most impressing. This is why I put this in, because, like, this impresses me a lot. I mean, it's not even text, it's just a picture. Like, wow. Like, it's not just saying that, it's not just regurgitating stuff that's already in the picture too. Like, it knows that it's depicting an architecture of a neural network generator, even though, you know, the word neural network isn't anywhere in it. The word generator is in it, but like, it came up with the word neural network on its own. And it came up with generative adversarial network on its own too. Like, that's nowhere in the image, those words. And it was able to come up with them. That's absolutely mind-blowing to me. Like, it is legit smarter than I am with this. Like, if you showed me this tomorrow, even after making this whole video and me, you know, having read this, and certainly if you showed me this when I was done finishing the book, because, you know, I can't remember what the first 2 chapters were about, you know, I wouldn't be able to tell you that this is a typical structure of a generative adversarial network generator, where random noise is transformed through a series of dense layers to generate a desired output vector. Like, that's absolutely, like, random noise is in there, input vector is in there, but transformed through a series of dense layers. I mean, the word dense is there. Layers, the word layers is not in there. Transformed through a series of is not in there. Like, it had, like, the fact that it knew that it was transformed through a series of, I feel like has a lot to do with this arrow here. Like, it knows what this arrow means. It means that it's being input through all these layers. I am very impressed by that. All right, so this did 8 minutes. Looks good. Yep. So now we're going through. We should get this output wasn't there already. Will not use since it doesn't match the criteria. Okay. All right. Well, it's still going. Okay, so I can get more reading done. One important thing to note about the generator is the activation function of the last layer. We can see we have selected TANH. One property of the latent space is that all values for all 512 dimensions are within -1 and 1. We could have left the last layer with no activation function, which is common when we simply want to generate numbers, like in a regression case. But that would certainly result in the generator producing randomly high positive or negative values. The training process of the GAN may teach the generator to produce only values in the -1 to 1 range. But we are making it more difficult for the generator to realize about that. For that reason, we are guiding the generator by configuring a TANH activation function that by definition will constrain the produced values to a range of -1 to 1. This will help the vectors produced by the generator to look more like a log in the latent space, and hopefully with some additional training to really look like a real log. Now let's look at the discriminator. It is also a simple architecture as depicted in the following diagram. Alright, so paste that in there. And now I bet you it'll do even better because it has that prior prompt.
The second image depicts the architecture of a neural network discriminator. Here's a breakdown of its components. Input vector. The input of the discriminator is a vector from the latent space with dimensions 1 times 5121 times 5121 times 512. Dense layers. The first dense layer transforms the input vector from 1 times 5121 times 5121 times 512 to 1 times 10241 times 10241 times 1024. The second dense layer reduces this to 1 times 5121 times 5121 times 512. The third dense layer maintains the dimensions at 1 times 5121 times 5121 times 512. The fourth dense layer reduces it further to 1 times 11 times 11 times 1. Output vector. The final output of the discriminator is a vector with dimensions 1 times 11 times 11 times 1, which typically indicates whether the input vector is real or generated, usually 0 or 1 in binary classification. This structure is typical in a GAN, generative adversarial network, discriminator where it takes an input vector from the latent space and processes it through a series of dense layers to produce a single value indicating whether the input is from the true data distribution or generated by the generator. If you need further analysis or have additional questions regarding this architecture, feel free to ask.
Alright. Went over my head. This is taking way too long. Oh, you know what? This is the one where this is going to take 5 minutes per epoch. So, like, yeah, of course it's stuck on this one. Oh, shoot. Okay, well, you know what I could do is I could stop it. Yeah, it's going to take 5 minutes per epoch. We can see we're on epoch 1 of 20, and we've already spent nearly a minute on it. And we're going to do 20 of them. So, bring out the calculator here, because I'm from the USA. So 20 times 5, which, yeah, it's 100. Yeah, so like almost 2 hours, pretty much, like an hour and a half for this. Like, no, that's not acceptable. So, yeah, this is just for one epoch, and we're meant to do 20 epochs. So we're going to have to... I'll just let this one epoch run, and then when I come back, I'll have to change that. One relevant point to note is that in the last dense layer, the one that produces as an output a number that represents the probability that it is a fake log or not, we have not configured an activation function. Usually, in these cases, you would find a sigmoid activation configured, which ensures the output has the form of a probability, a real number between 0 and 1. However, in this case, since there is no activation function, the output will be a real negative infinite and positive infinite. Why is that? Well, as I mentioned, training a GAN, generative adversarial network, is a bit of a special process, and we have broken it in pieces. One of the pieces is called the calculation of the loss. The loss we are going to use is a binary cross entropy, which basically will compute the distance by comparing digit-wise binary comparison between the real data, the labels, and the predicted values. That is the theory. In practice, we are using a function from the TensorFlow framework. There we go. This is a function that, if provided with the two vectors, produces as output the binary cross entropy loss. That rhymes. Very nice. However, it has two modes of operation. With from underscore logits equals true or false. When from underscore logits equals false, it expects the predicted vector to be in the form of values from 0 to 1. When from underscore logits equals true, it expects the values of the predicted vector to be real values between negative infinity and positive infinity. Basically, when from underscore logits is set to true, it will internally do a sigmoid equivalent to turn them into 0 to 1, and then do the binary cross entropy calculation. Why is this relevant? Because it is what is recommended in the TensorFlow documentation, but unless you are familiar with that, it is not intuitive. My goal with this use case and this book as a whole is to help you build the intuition that this is non-intuitive. So you might be confused by why there was no activation function. The reason is because TensorFlow recommends it when you use binary cross-entropy loss by setting from logits to true. You could configure a sigmoid and set the parameters to false and should still work, while perhaps will converge more slowly. Given that we understand the type of loss, now we will configure a function to actually calculate the discriminator loss. All right, that looks good. Let's check back in on the Google Colab. Okay, so now we did make it to Epoch. Nope, we're still on Epoch 2. I thought we made it to 3 already. So, yeah, it's just not... It's just not fast enough. Okay, so I will hit stop on that. And then we can't do that anymore. Yeah, we can't do my model dot save. We can't do. This should fail out. I don't know why it's taking so long because it should just fail out. Huh, that's weird that it takes so long. Oh, this is kind of cool. It shows you all the... Oh, well, that didn't fill out. That actually... Okay. This is cool. It shows you everything that's happening. So you can actually open up the code that's running. Oh. It looks like Google Colab can't handle it either. It used all the RAM. Well, maybe we can use something that has better RAM. Let's see. Yeah, so we've got 12. That's actually less RAM than I've got on my machine. I've got at least 16, at the very least 16. All right, so let's switch to a different runtime, maybe one that has more RAM. Okay, so now we're using TPU version 2. There we go. And now we've got a lot more RAM. Hey, more power. It's like that show Home Improvement. All right, so restart session and run all. Now it should go very fast. Yes. All right. Yeah, look at how fast it goes now. So, yeah, we're only at 4. Before we only had 12. So if we see this spike above 12, then we know we're working. What? This is interesting. I didn't have that error before. Huh. Oh, what? Oh, no, this is leftover. This is a stale one. Stats models. None of this is installed. Huh. Well, yeah, so I don't have any of some of these libraries, so I guess I'll just add them here. So we're going to pip install TensorFlow. Okay, we're going to pip install, I don't know, yeah, progress bar. Look at that, it auto completes it. That's pretty good. And then we're gonna pip install. It's not auto completing the stats models though. Maybe because that I already have that one. All right, so now it ran without the error. Take a quick pause. We'll be right back. All right, I'm back. So let's look at the notebook. So yeah, now we're at the slow one. That's just going to take some time. So moving on. The discriminator is going to be fed both with real logs and with fake logs generated by the generator. The function will receive two input parameters, one that corresponds to the output of the discriminator when real logs were offered, real_input, and one when fake logs came in, fake_output. Likewise, we need to compute the loss for each of the cases. We know that the loss must be computed against our expected labels. We know the labels because we know the class. We have two clearly differentiated vectors. Hence, to calculate the loss when real logs are offered, we compute the cross entropy between the vector of ones, label equals 1 refers to the log is real, label equals 0 refers to the log is fake, and the predicted values, real_output. One important note, you may have seen the way we create a vector of ones. This function is producing a vector of ones of the same dimension as the real output, which now acts as our labels to compare against. Ideally, the real output should be all ones in a perfect scenario where the discriminator identifies all real logs as real. However, strictly speaking, the output of the function above is not a vector, it is a tensor. And what in the world is a tensor? It is the data structure used by TensorFlow. So far, we have not been exposed to them yet because we were pushing arrays to our models and getting arrays as output. In this use case, we have decided to decompose the training process in its different steps. In doing so, now we need to deal with the internal data structures TensorFlow uses between those steps, and those are tensors. I will not go into the details of it. There is plenty of documentation. I just want you to be aware that the moment you look inside the models and try to get output from intermediate layers, etc., what you will get is the tensor format. There are ways to transform a tensor into a normal NumPy array. We used one earlier. So this is a tensor. We did not use the predict method, simply evaluated the model with the data, and that produces a tensor, not an array. By calling the NumPy method, we obtain an array from the tensor. Now let's look at the generator loss. In the generator, we are only interested in the loss of the discriminator with respect to the fake logs. But while in the discriminator detecting a fake log as fake, label equals 0 is a success. For the generator, it is a failure. The generator needs to learn how to confuse the discriminator. Therefore, the generator loss will look like the following. There we go. All right, so then let's do that there, and then we're going to do that there. Oops, and I added a new a new one there, so I can delete that. And yeah, this is going to take a while. I'm kind of curious if it crashes, so I'm going to keep it going. If the fake output from the discriminator is 1, it will be a success for the generator. Therefore, we will compare against a vector tensor of 1s. We need to create the optimizers now. The mission of the optimizers is to update the weights in the model once a training iteration happens and gradient descent is calculated. Atom optimizer is frequently used. Atom optimizer will dynamically adapt the learning rate, but it receives an input parameter of the starting learning rate. We configure a checkpoint that allows us to save certain data from all our models and variables as the training process evolves. This is optional but useful so that we can track the evolution of the process afterwards. The following variables help us control the execution process. The seed is a randomly generated vector that will be used to produce samples from the generator later on. Let's look now at how we have decomposed the training process that before was simply hidden behind the .fit method. The above function will execute one single training step. Therefore, you may expect somewhere later in the code there is a loop process that will run this function multiple times. Let's review what is happening in this function because it is the most important in this whole GAN puzzle. Some vector with random noise is generated. It will be used as input for the generator. We tape a set of functions that are executed because this will allow TensorFlow to be able to compute the derivatives and execute gradient descent and backpropagation. For now, simply consider that this is capturing the execution of the subsequent functions to be used later. The generator is invoked to produce a batch of fake logs. The training parameter indicates that we will be updating the weights as associated with this produced output. Now we ask the discriminator to take the batch of real logs perceived as parameter in the train_step function and evaluate them. And this is another really nitpicky thing. These would not be parameters. These would be arguments. My understanding of the difference between a parameter and an argument is when you define a function, you give it parameters. But when you call a function that's already been defined, when you use the function, you feed it arguments. And then the arguments are treated the way the parameters are treated in the function definition. Next, we ask the discriminator to do the same with the just purchased fake logs. Both models have run. It is time now to evaluate the loss based on the output they produced. Now that we have the loss, the next is to compute the gradient descents based on such loss so that the weights in the model can be subsequently updated. The following two functions will estimate the gradient descent given the loss just calculated and the trainable weights for which we need to calculate an update. Each of those variables will have its own gradient descent estimated. There we go. Once we have the gradient descent, we need to update the weights. That's what the optimizers are for. Given the gradients calculated and the trainable weights for each model, the optimizer will estimate and update the weights for that model. All right. Hooray! Okay, so that's done, and this is one notebook behind. So we're only at 5.3, thankfully. 5.4 now. Yeah, so I have 16 as far as I know on my local, so take quite a bit longer. Okay. Yeah, so here's some of the... So we're coming across that problem cell here. We should see this number go crazy. It should go way beyond 16 because it was crashing my local hardware. And then it was also crashing the lower tier version of the resources they had. So already we're at 8, so we're getting up to that prior problem. All right, here goes. Yep, so now we're at 10. Goes any higher than that, it's going to crash the... It would crash the kernel of the other one, but now we're using one with 334.6, so we're good. But here we go. We're about to crash the kernel of the non-advanced one. Yeah, the ETA for this one epoch out of 20 is 6 minutes. And there we go. We broke the bank. For my own personal PC, I cannot do 23.3. I do not have that much RAM. And then for the free version, it has even less RAM than that. So we're running steady here at about 24. So we're good here. But yeah, that ETA of 6 minutes per epoch is just too long for me. So I'm going to stop it. And now we notice that when I stopped it due to a keyboard interrupt, we're still sitting high at that 24. So that's what was happening, even though I would stop that cell, even though I wouldn't even run that cell. Just the more objects we create using our libraries here, the more RAM we accumulate over the course of the notebook, and there's a point where we're getting to 25. We'll probably even get higher than that. And I've only got 16 as far as I know. Yeah, so we're up to 27 now. All right, moving on. And this will end one-step training with the weights just updated to a new set of values, both in the generator and in the discriminator. We have the following auxiliary function that will help periodically generate, visualize, and save generated logs so we can observe the evolution of the... Oh, it looks like there's kind of an error there. The next function is the global function we will call to execute the overall training. Visualize and save generated logs so we can observe the evolution of the function. I guess it doesn't complete that thought. The next function is the global function we will call to execute the overall training. Given the number of epochs provided as an argument, the function will execute the training for that many epochs, and in each of them, it will load a batch of logs using the load_batch function described earlier. Then it will execute a train_step as a result of which the weights of both networks will be updated, and it will generate a set of logs after each epoch so that we can visualize how they look. At the end of the process, it will generate another set of logs as a final result. Let's observe what happens as we run the training. At epoch 0, the results are pretty random. Only the date and time seems to have some structure, but definitely everything else looks quite random. All right. At epoch 2, we start to see, oh, that's interesting. We start to see some familiar strings like BGP_MGR, but everything else is still very random. Oh, that's cool. You can see it. You can see it going through the process of learning. We can see over the subsequent epochs, how the log type area starts to oscillate between CFG underscore MGR, BGP underscore MGR, and other variations. The model is somehow trying to learn the path for the best realistic log. GANs have a challenge when there are various classes. They will tend to converge to only one, the most numerous. All right. Well, we're getting close to the takeaways. Hopefully, things. Okay. So yeah, this one is now done. So let's get our score here, and let's see if how that compares to the book. It should be a lot better because we're dealing with some. Not sure if the book must have changed their runtime type because we can see we're at 28 now, and we didn't have that much before changing it. So, yeah, I'm curious about that. Let's okay, but this was before switching notebooks. This is just a really dense, meaty chapter. So here we've got X-Train batch. Yeah, so it's way before that. We haven't even gotten to the graph yet. Oh, okay, so I think this is probably it. My model.layers, where is that? Oh, it's like way down here, I think. Huh. Okay. Well, I don't see that there. That's no good. So here's a my model.summary. There's the epochs. Yeah, I think this is the. So this is a categorical accuracy, which was 83. My categorical accuracy was it was a lot worse. All right. I wonder what their test score was. I don't see it. All right, so ETA on this is 2 minutes. I think that's fine. Let's continue on. At epoch 28, it is clearly generating a string that looks very similar to the interface down logs. The device and interface side is not properly generated yet, but everything else is quite accurate. You can run the training for more epochs and see if it ends up creating a better looking log. It is challenging to get to a perfect log because we are working on top of an autoencoder that is not perfect. The error introduced by the autoencoder cannot be solved by the GAN. But I hope you can see how a model like the generator that never saw what a log looks like has learned to generate a sequence of numbers that results in a pretty accurate log for a good part of the log length. But why is the GAN only generating one type of logs? Because those are the most numerous. Over the whole process of training, that circumstance results in the discriminator being better at dealing with that type of logs. As a consequence, it also produces more feedback to the generator, which will influence it to be better at generating more realistic logs of this type, so the end result is to converge to only one. The GAN specializes quickly in what produces the fastest gains. I was not intending with this use case to get a perfect sequence of logs, but to help you understand how GANs work and how they can be configured, leveraging a use case that is familiar to our industry. GANs are being used, or at least explored, by networking vendors for similar use cases to generate new data for simulation environments. Yeah, that's cool. You can kind of imagine that. It's like, an AI can produce a series of log messages, and it can be like almost like a test question, like describe what happened here, and it can show you like a BGP withdraw message where like a route is no longer available and is removed from the table, and like it can be like a multiple choice question like the BGP port went down, there was a BGP update, some curveball ones like the kernel crashed, or some that are obviously incorrect. I could see. I bet you that is like one of the things they're probably going to do is like use AI for the Cisco exams. Oh. Wait, why is print log not? Oh, these were out of order for some reason. That's cool. It can kind of predict how long it'll take. Or no, it just shows how long it took last time it ran. Never mind. Which kind of serves to do that. All right, so the takeaways. The following are the main concepts I would like you to remember from this use case. There are multiple use cases in machine learning that are solved by combining various components and making them run coordinately. Autoencoders, GANs are examples. Data generation is a very exciting and growing discipline in the context of deep learning. Video, image, audio have been their main applications so far. Text generation is happening using other techniques, but GANs can also be applied, as we have seen in this example. Autoencoders are a very good tool to encode very sparse matrices, like the ones representing one-hot encoded text sequences, into a more compact and information-dense format represented by the latent space. Resources are always limited, and sometimes we cannot assume all our data for training can fit in memory, or even that we have all the necessary data. Therefore, incremental training helps us deal with those situations where the training happens as you go by loading either new data or batches of data from our training dataset. Further work. There are various areas to explore to improve the results of this use case. Some I would suggest. Test different architectures for the autoencoder, since the accuracy of the autoencoder has a relevant impact on the overall use case outcome. Experiment with incremental training on the autoencoder itself. Explore new ways to run the GAN. There is a concept called conditional GAN where we can introduce a new signal to the generator that somehow represents the class of data we want to generate, for example, the class of log. This signal would also be forwarded towards the discriminator. This helps to alleviate the issue that GANs converge to only one class normally. We can force it to generate data from multiple classes, in this case, multiple types of logs. Alright, so that's the end of use case 9. I still need to run the notebooks, so I need to run both of them. I feel like it's more trouble than it's worth. I'm not really getting that much out of running the notebooks. And then I wonder if that 334 limit is even too low, because as I run these, we're climbing higher and higher. We're now at 30, which is a long ways off from that, but it's that's the point. AI applications are very, very power hungry. Oh, so we got an error here. Okay, we do have one of the graphs. So load data takes 2 positional arguments, but 3 were given. Oh. Yeah, there's an extra. All right, so use case 10 is going to be that router is not properly configured, which is like a really good that's one, like, obviously that's a good one. Yep, I'll close that, and maybe we can try to get these going here. Yeah, loading the data isn't really working. The other thing to know is I don't have limitless space in Google Drive. So if this is going to create a bunch of files in my Google Drive, I will very, very, very rapidly run out of space there. So that's going to be a limitation as well to running these. And then, since I'm just using the free service, I'm very lucky to have this much horsepower, but I can't do basic things like run 2 notebooks at once. So I guess I'm willing to end the video, with the notebooks working the way they have been. I'm pretty satisfied with how things have been. I'm reasonably assured that the code will run, since we have the horsepower for it. It would be nice to troubleshoot why this was a problem. Let's do that briefly here. So that works, but let's take a look at the load data where that's defined, where that came from. Okay, so it came from here, so we got to give it a batch size. And I don't know if they meant to say 1.1 and they accidentally put 1 colon 1, or not colon, but parentheses. All right. Okay, so yeah, now things are working. Um, so we got another error here. Scatter plot. Interesting. So scatter plot only takes 0 to 1 positional arguments, but two positional and 2 keyword were given. So I think we have to change. We have to change one of these to a to keyword. So that should be pretty easy. Let's just do a help on help SNS dot scatterplots. All right, and let's comment this out first. There we go, and then we've got so latent embedded. That's the data, right? So the hue is there. Yeah, so we'll do data equals. Yes, I'm not a robot. And then we'll do maybe can we do data equals again? I'm confused there how that works. I don't think we can. Can we do data 1 and data 2? No. Let's try x equals. We'll do x and y. There. Yeah, and that's what the book looks like. So, yeah, it's cool. I like troubleshooting and resolving things. All right, so compiled metrics have yet to be built. Be empty until you build the model. So, yeah, I think I didn't train the model. You know, that's the thing where it's going to take 5 minutes per epoch, so I just didn't train it. All right, so there we go. So this should be done pretty soon. And the good news is it just is locked here at 32. So you could do a home computer for that. You could do 32 to 64 pretty easily, pretty cheaply. I wonder if mine's 32 actually. Let's take a look at that. Mine might be 32. Where is it? Huh. Other maybe? I'm not seeing memory show up. Computer maybe? Disk drives? Should be under its own category. Human. Huh. I guess I don't have any memory. I thought it would be under its own. It'd be like memory or something. It would show up as. Huh. Well, this is a good one for. Oh, maybe it's hidden for some reason. Let's ask ChatGPT. So, how can I see how much memory I have?
To view information about your PC memory, you can follow these steps. Using Task Manager, right-click on the taskbar and select Task Manager, or press Ctrl plus Shift plus ESC to open Task Manager. Go to the Performance tab.
Why was it missing from that screenshot? I want to see the particular hardware associated with my memory. I thought I could see that in Device Manager, but it looks like it's missing. Yeah.
It appears that memory, RAM, is not directly listed in Device Manager under its own category.
Oh, firmware?
Instead, memory modules are usually managed by the system firmware, BIOS, UEFI, and can be viewed in the System Information Utility or Task Manager, as mentioned earlier.
Oh.
Device Manager does not show RAM as a separate device category.
Why?
However, you can see some related information under other categories. To see detailed hardware information about your memory, you can try these steps. Check under System Devices, open Device Manager. Expand the System Devices category. While this doesn't show the memory directly, it can show related components like the memory controller. Using third-party software, you can use third-party software like CPU-Z or Speccy to get detailed information about your memory modules, including menu.
Why doesn't it show the memory? That would be important, wouldn't it? You want to know like DD3 or DD4, like why is it missing from there?
Device Manager in Windows is designed to show devices that have individual drivers and can be managed by the operating system, like processors, network adapters, and storage controllers.
Oh.
Memory, RAM, modules, on the other hand, do not have individual drivers that need to be managed in the same way, which is why they do not appear as separate entries in Device Manager.
Interesting.
Instead, the operating system and hardware interface, BIOS, UEFI, handle memory modules, and detailed information about them is available through other tools and utilities designed specifically for hardware monitoring and diagnostics. To identify the type of memory, e.g., DDR3, DDR4, and other detailed specifications, you can use the following methods. System information. Press Win plus R to open the Run dialog box. Type MSInfo32 and press Enter. In the System Information window.
Alright, so the memory... Alright, so I guess it's fair to say that the memory doesn't even plug into the operating system is why you can't see it there. The memory is something that plugs into like the BIOS or like, you know, the stuff other than the operating system, like the UEFI. So it's like the memory, and that makes sense because you have to have it separate from the operating system, otherwise you couldn't boot the operating system. So like it makes sense that like certain components such as the memory couldn't be shown there because that's how the operating system is running. So like it'd be hard to pass that information from one system to another.
Exactly, you got it. Memory, RAM, indeed operates at a fundamental level within the computer system architecture and is managed by the BIOS UEFI firmware rather than the operating system itself.
Alright, this is done.
Here are the key points that explain why RAM is not shown as a separate category in Device Manager. Hardware initialization. RAM is initialized by the BIOS UEFI firmware during the boot process. The system firmware detects and configures memory before the operating system loads.
Alright. And let's connect to a hosted runtime. Oops. Let's change the runtime type. We gotta use the big beefy one. Alright. Get this one to run all the way through.
This is essential because the operating system itself relies on RAM to function. No drivers required. Unlike most other hardware components, RAM does not require device drivers that need to be managed by the operating system. Device Manager is primarily for managing hardware devices that require drivers. Firmware management. The management and configuration of RAM are handled by the system firmware, BIOS, UEFI. The firmware provides the necessary information about the installed memory to the operating system once the system has booted. Low-level functionality. RAM operates at a very low level, providing the working memory that the CPU uses to run applications and processes. This level of functionality is abstracted away from the operating system, which relies on high-level abstractions. Because of these reasons, RAM is now listed as a separate device in Device Manager. However, the operating system does have access to information about the memory, which can be viewed using tools designed for system monitoring and diagnostics, as previously mentioned. This separation of responsibilities ensures that the system can boot and operate efficiently, with the BIOS UEFI handling the low-level initialization and configuration of hardware components, including memory, and the operating system managing higher-level functions and devices that require drivers.
Alright, looks good to me. Yeah, and then we're all good to go in the part of the book here. Use case 10 will be in the next video. Well, we got an error again. From progress, but yeah, so we forgot one. Oh, yeah, good. Okay. Ah, another error. No module named progress bar. Why not? Oh, because I misspelled that. There we go. Simple errors have simple solutions. All right. Oops. We got a problem here. Uh-oh. That's not good. Why doesn't it have that? Should have it right here. Okay. Do I need it? I don't think I need it. I think this was to load in existing ones. Yeah, everything's running fine. Forget wacky results and we'll see. Oh, I got an error here. Oh, yeah, okay. So that's wacky results. Alright, so we have to get that cell to work. This one here. Shoot. I don't want to deal with this. It's not worth it. Ow, and I just pinched my foot really badly. Alright, so I think I'm gonna call it because it's just not worth it. Maybe I can try this in double quotes. That might help. I don't think it'll make a difference. It's Python, it won't make a difference. I'm just concerned that it's not properly completing that. Yeah, it's saying it doesn't have this file in there. Which, I mean, we can check, right? Well, I don't know. I don't know if it has it. I think that's it. It doesn't matter. We can take the L. We only had to take the L like once or twice, so it really doesn't matter. Just to run that through. We know what the problem is. That file is missing. We just need to add that file or fix that in some way. So Yep, that's it for this video. That's it for use case 9. So thanks for watching, and stay tuned for the final use case. Ooh.